That's what you call it if you normally say you have a team of, I don't know, 100 people, but some days you just have very minimum amount, just enough to have the most important things covered, like maybe 10 people, called skeleton crew. So today it looks like we got the skeleton crew. Okay, yeah, so we're done with all of the new material. Right, so I think this is just for questions and answers, hopefully answers. Questions and hopefully answers.
You have some give us some suggestions about bullet 3 and bullet 4.
Okay.
It kind of really stuff and we figure out.
Okay, sure. Also, we should. I've been kind of delaying the decision about exactly how we're going to wrap the course up. Because the end of the time has been so unusual and it keeps changing, different appointments and so forth. So right now, what I'm thinking is that we can extend the deadline for at least a week or two. Maybe you can send them to me by email because it's definitely too late now for me to finish grading them before I leave anyway. So if I'm not going to finish before I leave, you might as well take another week. There's an old saying which I believe very much. It's much better to be correct than to be fast. So I'd rather if you go a little bit slower and make sure that you understand everything. Yeah, I don't want you to rush and not really understand it. So it's okay with me. So today's the 22nd. Yeah, do you know if there's any problem on the TNUT side? Like, is there a deadline when these grades should be submitted? Do you know?
It's set up by the
Okay. So my idea is to wait as long as I could wait 2 weeks, and that's okay with me. I have a crazy schedule when I first get home also. So I have a very long trip to get home. It's more than 30 hours. When I get home, I'll need to sleep. I have an 11-hour time change. 2 days later, I start teaching the course at my university. And then I have to go to Washington for some meetings with the government. All in that first week. So I won't do anything until the week after that. So the Monday of that week is, I know 29 of August. I'm just thinking of Mondays. So next would be September 5. This is a U.S. national holiday. So we can't have it do all that. So let's try 6, 7, 8, 9. I don't know. How about something like September 9? So from today, that's 2 weeks and 4 days. Try to think of the best way we can do the email section too. Because it's easier for me if everybody can put their things into one file so that I only have to download 40. Instead of if each person sends 5 or 10, I have to download a few hundred. So the other thing would be a Dropbox. Did anybody use Dropbox? Media file, that's another file. That's like Dropbox, something like that. On the Dropbox site or on media file? For you? Okay. I've never used media file, but I can look at it and figure it out. So it's called media file. Capital, like that? Yeah. Media fire. Okay. Everybody already knows how to do that? So I just have to learn. Okay. All right, so I'll try to look at that either this afternoon or in the morning, and if I have any questions, I'll let you know. But let's plan on the deadline is September 9 and submit through MediaFire. Okay? And you're going to submit the things that are called homework and problems. These two kind of go together. And also projects. Then we'll submit exercises. Okay. Thanks. Okay. We're just discussing how we're going to end the class. So we tentatively agreed that we'll have a deadline of September 9. So that's 18 days from now. For this class, for higher level language. Right, so that way everybody gets a chance to make sure they get all the projects working correctly. Take your time so you know to write. If I understand correctly, the next AP class probably isn't until December, right? December, yeah. So what happens between tomorrow and December? You're not sure. Okay, so well, I can help you out for 2 weeks. You can keep working on MATLAB or C++ programs or Excel. Yeah. Yeah, I know it's a little bit unpredictable. Yeah. At this conference on Friday, they asked me for my suggestions for the AP program. One of my main suggestions was to try to make it more predictable. Yeah, I know it's got to be very difficult for you students. I mean, it's hard for me to imagine if I was in your position. You don't really know when the next class is coming, whether it's short, whether it's long, who the teacher is. Okay, so I will submit through MediaFire.
We send the link on the email so that the link to the MediaFire.
Okay, you can send it to me.
Send the link to the MediaFire and you can download it.
Okay. Yeah, that'll work great for me, I think. Okay, good. So now I think finally everybody has a copy of everything, I think. Is there anything that you think you're missing? You have the textbook, you have all the recorded lectures, the PowerPoint, copies of all the exercises, copies of all the projects, copies of all the homework.
So what about the final exam?
Oh, that's a good question. Yeah. Yeah, they're going to get the final exam after I leave. So I think the final exam, I think you might as well do all this first. So how about if we had the final exam on Monday?
This month?
No, September 12th. How does that sound? Actually, let's have it September 9th, the same day. Finish all the projects by that day, and that will make you ready for the exam. So let's say September 9th. How does that sound? Okay.
And what will you do like in the exam?
Yeah, what would the exam be like? Yeah, it's going to be, it won't involve any programming. All of the programming that you do will be in these projects. So it will be 100% paper. And most of it will be a combination of, I might ask you to write down some code as if you were writing a program for some things. And in other places, I will give you some code and ask you what would the outcome be if you put this in. Okay. So those are the two main kinds of questions. There will be some logic questions. There will be some, for like if and else if and end. But it won't be very difficult. I don't think. I hope it won't. It won't be difficult for me because I don't have to think.
So what if we put it earlier? Like one day next week?
You'd rather have the exam sooner?
Because of the longer it takes,
The more you forget.
more complicated.
Yeah, but you also though, I think it helps if you can finish all your projects first, because that forces you to learn everything.
Yeah, I think so.
So if you can finish all your projects by next Monday or something, you can do the exam on Monday. That's okay with me. It doesn't really matter when the exam is. Who would like to have it sooner than September 9th? Who wants it earlier than September 9th? Who likes September 9th? Yeah, it seems like most people like September 9th. Yeah. Did you vote, Alex, or do you care? Yeah. After the deadline? Yeah. Yeah.
Maybe just leave them all the job for just as
Never decide on the days. Yeah, actually, the day of the final exam isn't very important to me personally. I would think if I were you, I like this idea that I will finish all of the homework and all the projects, because this should be the best possible preparation. So if you understand how to do all of these things, then you should be ready to do the final exam. So I personally think that's good for you, but it doesn't matter. If you really want to take it earlier, that's okay with me. Okay, so for the late comers, I'll just go over really quickly one more time. We'll discuss at the end of the course. So we've agreed that September 9th will be the deadline for handing in all the homework, all the projects, all the problems. Okay? Homework, problems, projects. Don't submit exercises. You'll submit them via MediaFire. Apparently that's something everybody knows how to do. And now the other thing we're discussing right now is when they have the final exam. And I said, it's okay with me and I think it's a good idea, if we have it right after the deadline for all the projects and problems, because then you will have finished everything, you should be ready. That should be good, like you said. But a couple people have suggested they would rather take it sooner. And I'm flexible on it. We did have a vote. The vote so far said have it on September 9th. Okay. Okay, any questions about this? I hope the class has been fun. I know that computer programming is often frustrating. It's frustrating for everybody who does it. Sometimes you're trying to get something to work and it just seems impossible. But in the end, I mean, it's really cool. I think it's cool that you could, with a few simple commands now, you can get the computer to make millions or billions of calculations. And if you program it correctly, those calculations are actually useful. So it's pretty cool. We didn't talk about release. That's something you can still look at on your own. I think you could have fun with that. So you can still look into that if you want. There's also MATLAB can be embedded in other programs that have more graphics themselves too. MATLAB just becomes a set of commands inside of other programs. So we won't worry about that now. We're just concentrating on MATLAB. questions. If there are no questions, we can all go work on the projects. Any questions about Excel?
I have a question.
Okay.
On the exercises, the last exercises. This using
Okay, maybe we can get out to inspire this up. Put it up on the screen. Yes. You put it up. So because I go home in a couple of days, I looked at the weather report for the area around my house. The high temperature tomorrow in the daytime is 19, at night 8. So quite a big change after being here.
May I question?
Say it.
As I know, Simulink is a new library from the lab. So may you introduce this for us because it is very helpful for engineers.
Yeah. I mentioned about GUI. GUI can be part of what's called Simulink. And Simulink has a lot of features that are particularly useful for simulating dynamic systems and control. So there's something called a block diagram. It takes a while to learn exactly how to use this, but the concept is fairly straightforward. So let's say I had let's say that we wanted to simulate this system. There's a mass, it's sliding on a surface with mu, and there's a spring connecting it to the wall, and there's some force acting over here. Okay. Then a block diagram for this could look something like this. I'm just going to draw it to give you an idea. It's coming in with a plus. It's coming in with minus, and that one with minus. Okay, so this will make the most sense when it's all done. If I describe it piece by piece, it's going to be difficult. Okay, but I'll start with the F here. And this thing right here, the circle, this is called a summer. And it doesn't mean this time of year. It means something that takes the sum, mathematical operation. Okay? So this says plus, minus, minus. So those three things, this one with the plus sign, these two with the minus sign, if you add them all together, produces this thing. Okay? This is going to be MA. Alright? This one is going to be K times X. This is going to be mu times X dot. So F minus mu X dot minus KX is equal to MA. A is X double dot. That's the equation, because we know that this is mx double dot plus mu x dot plus kx is equal to And then I can put another operation on it, which would be the integral dt. And that would, well, let me leave this as x double dot. That would give me x dot. So I take x dot and I pass it through another block. And this could be the value of mu. And then pass this through another block to do another integration. And this becomes x. Take that, pass it through the block up here. It's k. Now this block diagram represents that equation. Okay? What's nice about Simulink is, in Simulink knows how to do the calculations for all of these types of operations, including this one. So in Simulink, you can create a picture that would look something like this, and then you can run that, you can click a run button, and it will execute a program that will solve this system. So it's sort of like ODE 45, except you never put in the equations, you just fill in these blocks. So it's very, very, very easy to use. Okay? And then if you want to tweak something, like if you're doing a design, maybe you want to know what changes. If you want to change the value of k, you can just go right in this block and change the value and see the output change. Or you can change the value of mu, you can change the value of f. Okay? So that's the idea of a block diagram. Maybe in a year or a couple of years I'll be able to come back and teach a course in controls. This is my specialty, and I really like controls. But with control systems, you typically use something called PID control. I don't know if you've ever heard of these. But the idea with a control system usually is that you have some dynamic system. You put an input in, so I'm going to draw a new block diagram. Here's an input. It goes into the system. And here's the output. Now, the output is something that you know what you want. Like, for instance, if I'm trying to land an airplane, I know that I want the plane to be at a certain altitude, a certain speed, and so forth. But this output here, what I'm actually measuring here, would be the output of the actual system. So let's say it doesn't match the thing that I want. Then what we do is we create, with the summer, this is the actual output. And over here, we have our desired output. So I put them into a summer, one with plus and the other with minus. Okay? And then what this would be what's called error. Right? If I take what's actually happening in the system, like how high it is, then I compare that with what I want to happen, the desired output. The difference between those two, this is a summer, so it adds them all together. So this is equal to plus that one minus that one. So if the desired output is exactly the same as actual output, the error is 0. But if it's not true, the error is something that's not 0. Okay, how do I fix the system? I fix it using what's called proportional integral derivative control. So I'm just going to describe the words. I can't do a whole course in 10 minutes, but proportional control means something happens to the system, something comes out of the controller that goes into the system, and that thing is proportional to how big the current error is. So let me give you an example of that. Suppose that we had a variable heat output heater in this room, and it's cold outside, and we want the room to get warmer. All right, so I come in, and the outside temperature, let's say, is 10, and I want the room to be 20. When I first come in, the room is 10. I set the desired output to 20. So now I'm putting 20 in here, and the actual So the difference between those two is 10. That's the error. So using an error of 10, it commands the heater to start putting out a certain amount of heat. If the heater works, then the room starts to warm up, and the error can slowly go down, because 10 will change into 11, change into 12, change into 13. So in the end, when the actual output gets close to the desired value, the amount of heat coming out of the heater will go all the way to 0. If it's proportional to the error, then it only puts an input in if there is error. If there's 0 error, something times 0 is still 0. Okay? So the idea with proportional is that you should put an input in that's big or small depending on how far away from the right answer you are. How far away are you from the desired output? If it's a speed control for a car, it controls the gas in the car. Right? If you set the speed control to go 30 kilometers an hour, well, 80 kilometers an hour, you set it for 80, and it measures how fast you're actually going, and it only measures 40. That's a big difference, 40 kilometers per hour. So it gives a lot of gas. But if it measures 78 and you set it for 80, then it gives almost no gas because you're going almost the right speed. Okay? So that's the idea of proportional control. So what are these other two? Let's go back to the heat example. If the outside is 10 and the inside of the room is supposed to be 20, that would mean a difference from the inside to the outside of 10 degrees. And the room is not perfectly insulated. So that means as long as the room is warmer than the outside, there's always some heat that's going to leak out past the window, past the wall. So to keep the inside room temperature constant, will still require some heat to come into the room. But if our heater is proportional, it will only put heat into the room if there's a difference between 20 and the actual temperature. Okay, so we started with 10. We want 20, that's a big difference, 10C. The heater puts out a lot of heat, but as this number gets bigger and bigger, the amount of heat coming out of the heater gets smaller and smaller, and we're losing heat to the outside. And somewhere before this gets to 20, it balances, and then it can't get any warmer. The amount of heat coming out of the heater is only equal to the amount of heat we're losing through the wall, so we're stuck at something like 18. So proportional is a good idea. Put in a big input if you have a big error, put in a small input if you have a small error, make it proportional. But it can't give you a 0 error, because in order to get an output, you have to have some non-zero error signal, because it's proportional. Okay, so integral fixes that. Integral takes the integral of the error signal with respect to time. So if the error signal is not 0, even if it's really small, if you wait for a while because of the integral, somewhere with a curve, the integral gets bigger and bigger. So then the integral will start to command the heater to give out more heat because the integral is getting bigger. And that way you could actually get to 0 on the error, but the integral is not 0. So that integral can tell the heater to keep putting heat out even though you're exactly 20 degrees. So an integral control gives you the chance to get right to 20 degrees. Okay? And derivative control does the opposite. The idea with derivative control is that look at the rate of change, the derivative of the error. And the reason why you put that in is to help the system be more stable. Right? So let's suppose that you've got this nice big heater. You want the room to be 20 degrees. The current temperature is 10. So you tell the heater to put a whole lot of heat in. And if it's really a good heater, maybe it zooms the temperature way past 20. And it ends up going up to 30 or something like that. And then it has to turn way down, and it zooms back down, and it goes past 20, and it cools off to 10 again. So it's very unstable. So the idea of the derivative is, if it sees that it's got a good slope, and it's heading towards the right answer, then it slows down the controller. And says, you're going to make it. It's kind of like you with the gas pedal, right? If you're coming up to a stop sign, and you see it in the distance, you don't need to give any more gas. You can just take your foot off, and you'll still coast all the way to the stop. So that's the idea of the derivative. So that's one semester long control system in about 5 or 10 minutes. But the reason why I mention it is, when people represent control systems, let's say we're going to make a proportional controller to the Kx, to the spring force. So this tells me where to put it in. So I can add a controller over here based on that error signal. Or if I want to make a controller proportional to the friction force, I could add another controller over here somewhere. So the advantage of Simulink is, with a block diagram, I can decide mathematically where to add a controller, and I don't have to do the math, because MATLAB knows how to turn this picture into the correct equations and then solve. All right, that was a long answer. Yeah. No extra charge. Okay, so let's see what we got here. You were asking about number 5?
Yeah, number 5.
Add another column to the sheet that prints a y if the y value is largest, a z if the z value is largest, or a w if the w value is largest. Note that you may find it easiest to use the Boolean operators of and or. Use the Excel help query to learn how to use these functions. Also, you will need to nest additional if statements inside the first if statement, since Excel doesn't have an else if function. Yeah. Okay. Because you can, Excel also has, I think they're called character, like C++, right? Excel has character values like C++. Same concept as string in MATLAB, character in C++. So here, I don't think you want to use greater than. You would want to check equals between two character variables. So this is supposed to, it prints a y if the y value, oh, I'm sorry, if the y value is largest, I'm sorry. Okay. Yeah, so you do have to compare numbers. Okay, I'm sorry. So what was the question again?
The question is that how to use that? I put the help, use the Excel help. When I write the help and come up with something that is very good, and say it's how deep is really big.
Okay, well let's go ahead and let's look at help together and see what that. Yeah, we need to search up here. Search the diff. Okay, so if the logical test, the value of true, the value of false. Yeah. So you probably want to do something like, actually similar to what it's saying, right? So you could put in a logical test, and then you can put whatever you want the argument to be. What if the test is false or if the test is true? So you could have a statement like. If y is greater than z, and then the syntax is, this is what happens if it's true, and this is what happens if it's false. Okay? So what would you like to happen if it's true, let's say? You have three values, it's y, z, and w. Yeah, right? So you do have to nest the loops. Yeah. Yeah. So what if W is bigger than Y? What if W, you're supposed to print which one of these three is biggest, right? Yeah. So you really need to do two tests at the same time. So you could do something like this. If Y is greater than Z and Y is greater than W. I have the syntax wrong? Yeah. I've never, I'll be honest with you, I've never used this command, but, so it looks like this? Something like this? Okay. So if that's true, then you would print Y. Yeah, and now if it's false, another if, right? If Z is greater than W, this is probably the easiest thing to do. And you can print Z. And if that's not true, W. Yeah, that looks like it should work. That doesn't work. It's not very useful. I don't think you put equals in there, do you?
So what is exactly P stick P stick and C stick and
Yeah.
D stick. Why is
Yeah,
that?
but also I'm not sure you put equals. Do you use equal sign in the function? I don't think you need them, but I'm not sure. That's okay. That's okay. That was okay. Over here you need, yeah. I think the equal sign, try taking out the equal sign. Yeah. Oh, you're right. Okay. You should have formatted the end, is correct? Let's check the end function. Yeah. That's okay. Yeah. Maybe
Let me open what is done.
okay. It's a double quote. Yeah. It's a double quote, not a single quote. Sorry. Yeah. Yeah, it's kind of interesting. I mean, a bunch of people sat in a room and decided what the syntax would be when you get to these languages. So it is kind of interesting that, you know, some of them like to use a single quote for something they call a string variable. They use double quotes, they call it character variable. And it's kind of interesting that they don't all have the same, you know, same definitions. Okay. Any questions about the logic of this? That's pretty slick. I mean, compared to C++, this is probably more efficient for this kind of statement, for that kind of sorting. I did, one of the things I did in Excel the last couple of years, a lot, is sort of like this. So, I don't know if you're interested or not, but if you like me describing real world examples, I can tell you about one more that I did. Okay, so I worked for the main science funding agency in the U.S. government. So people would send proposals, just like you did this morning. And we would decide which research projects we would fund and not fund. But we use a big system of what's called peer review. We talked about peer review in the 140 class a little bit. So usually what would happen is, I might have, I'm just going to make up the numbers. I'll say I have 15 proposals. Each one needs a minimum of 3 reviewers. Okay? These are the rules of the agency. It's supposed to be a fair competition. So you have to have 3 independent reviews for every proposal or more. So that takes 150. Okay. Now, we convene a panel of experts, and the panel would usually have about 10 to 12 proposals each. Okay, so take this 150, divide by, let's say we have 10 panels. Let's say we've got 10 panelists. We have 10 proposals per panelist. So I need 15 panelists. Okay, all the panelists would get invited to Washington. They sit in a big conference room, and they're going to discuss these 50 proposals. So then we make up the so-called batting order. So a total in this case of 50 times 15, 750 blocks. Each proposal gets 3 reviewers. So I have to select from the 15, 3 to assign to number 1, 3 to assign to number 2, and so on. But the 3 have 3 different jobs. One is called, I won't tell you what the names are, it doesn't really matter, but one is called lead, one is called scribe, and one is called just plain reviewer. So on every row up here, you know, maybe number 2 is going to be the lead, number 7 is going to be the scribe, and the last one is going to be the reviewer. And then you go to the next row, and there's an LSR. Well, when it's all done, each of the 15 panelists should have 10 proposals, and they should have about the same number of lead, scribe, and review. So it turns out with 10 proposals, and there's 3 of these, somebody's going to have 4 lead, 3 scribe, 3 review. Somebody else will have 3 lead, 4 scribe, 3 review. But they have to be sort of equal like that, okay? And this order, the order of discussion is somewhat arbitrary. It doesn't really matter which proposal we call first or second. After somebody does one of these jobs, there should be the next couple of proposals where they don't do anything. Okay, so if this guy's lead on this one, maybe down by number 4 or so, he should be scribe. In the meantime, I fill in these rows with other people. Well, this is really tricky to try to figure out how to do this. A lot of people, a lot of proposals. And we used exactly this kind of logic to count the number of L's, count the number of S's, count the number of R's, this big table, so everybody has about the same amount of work. You have 3 lead, 4 scribe, 3 review, 4 lead, 3 scribe, 3 review. And there's spaces in between them, so they get a rest in between 2 of them. Yeah, I did this once every couple of weeks for the last 2 years. An exercise sort of like that. And it's a lot like this one, except without the numbers, it's with these assignments. Always with Excel. We always use Microsoft Excel. Okay. Open for any other questions. Project 3. Can we put project 3 up? Homework 3 or project 3? You have project PA 3? This one? Yeah, okay. Yeah, so here's a block diagram, sort of. We were talking about block diagrams earlier. That's sort of a block diagram there. Okay. What's the question?
What's the describe and what's the answer?
Okay. Well, why don't I read through it and then tell me when you don't understand something. So, signal to noise ratio. Do you know what that is? That's very commonly used in electronics. Inside of an electronic device, there's voltage and current. So the voltage maybe is supposed to be 10, let's say it's supposed to be 10 volts. Actually, if you could measure it very precisely, it's not going to stay exactly 10 volts. It's going to have a little bit of variation in it. So if I plot it, say, if this is 10, probably if I measure it, even though it's supposed to be 10, it's going to look something like that. This squiggle is called noise. Right? It's error. So signal to noise ratio, this means, how big is this number compared to that number? And usually you like something, you want to have a value, it depends on the application, but the value may be something like 10 to the 6, maybe 1 in 1 million signal to noise ratio. Okay, but the value is a little bit arbitrary. I mean, it's not arbitrary, but it's affected by what the thing is that you're trying to measure and what device you're using. So I used the example on the airplane the other day, that the radar, the last digit on the radar corresponded to approximately 3 meters. So I'm trying to measure the position of the airplane when it's coming in for landing, but because binary requires a certain number of digits, remember they're all zeros and ones, and I have a limited number of digits available inside of the device itself, inside the radar itself, the last digit turns out to be a 0 means no meters, and a 1 would mean 3 meters. The next digit would be 0 is 6 meters, a 1 means 6 meters. Right? So 3 meters, obviously the airplane, 3 meters is a long distance on the airplane. Right? So that's a lot of noise. So whether or not the plane is between, let's say, 99 and 101 meters away, I would measure the exact same thing no matter where it is in that range, because the last digit's only good to 3 meters. And then maybe 102 to 105, it all gets measured as 103. 106 to 109, all gets measured as 107. Okay, that's a pretty big signal to noise ratio. I'm sorry, pretty small signal to noise ratio. That's a lot of noise in that signal. All right, anyway. So the signal to noise ratio of electronic devices is affected by the design characteristics of the millions of transistors in the device's circuitry. The two most influential design parameters are the gate oxide thickness, GT, and the dopant, usually arsenic or phosphorus, concentration, DC. All right, so I think this picture is totally unnecessary. I think it's pretty Right, so he's giving you some word description of the inside of a transistor. I'm not a transistor expert. I don't know. It looks like a little, I know if I take the back off of my phone or my computer, I can see the stuff in there. It looks like little circuits. So I guess some of that is gate oxide thickness, GT, and some of it is dope. Laboratory testing of devices generate data of SNR, signal-to-noise ratio, for different combinations of DC and GT. This laboratory data has been used to design cost-efficient transistors using design models. So you get a hypothetical data set. He describes the structure of the file. You will find that increasing DC or GT increases the signal-to-noise ratio, which is good. Signal over noise, the bigger the better. So anything you can do to make that bigger is usually good. And increasing DC and GT usually makes it bigger, so that's usually good. But if you use more dopant or thicker oxide, it requires more processing time, more raw materials, makes it more expensive. Your objective is to use this data to find the DC and GT combination that gives a minimum cost for a given SNR. Is that statement confusing, or do you understand that? Okay. We're going to write a C++ program that opens this data file and reads it into arrays. So have you done that program? To read the data into the arrays? Did you do that? Okay. Well, I'm going to assume that you're going to do that. Then you're going to use a void function, and you're going to find the slopes, intercepts, and R squared values, right? That's a function. R squared is standard deviation of the best fit lines, so that's a regression analysis of SNR, the Y data, versus GT of X for each value of DC. There are 5 values of DC. So in effect, you're going to be taking data for one value of DC, and you're going to plot SNR versus GT. Okay? And the data is in the table, so you get some points. And then you have to do a regression analysis to get the best fit line, straight line. And you'll get the slope, the intercept, and R squared. Okay? So you get the slope, the intercept, and R squared. Sure.
We have a slope each other here. That you have to find the straight line. So from the data for HBC, you have a slope and intercept. So this one here. When you have to find slope and intercept, so what is the formula for this one? Like this x, DC or here is for ZT, x is ZT, and y is S and R, and here is x squared. And this is all data. You have to find the sum of x. The sum of y also, and the sum of x squared. And the mean of x. The mean is the average. The average. So we have in this formula, that's it for, I don't exactly remember, but it's the sum the sum of x over another. I don't exactly.
Yeah, there's a formula. There's a
formula.
formula. Yeah.
So can I explain why?
Sure.
Why you have to find the rs squared. R squared is like r squared. B is equal to rx plus b. We have to write. And so x equal and y v. So a time n must be equal 1. That is a perfect line. So that's why we have to find r squared. I think it's in this one don't show it.
That's right.
So I think it's a big problem.
Yeah. Remember the reason why this might not be true. You have some data. So for each point, you have data that looks something like x and y. Then you have a model of the line. And maybe I'll call it y, let's call it y tilde, we'll have. And that's equal to the slope plus b. So what's the difference between the data and this model? The difference is the x's are going to make the same. They're going to use the same points, but the slope, this won't be able to predict all of the y's. So at each point there's an error. And that would be the sum of the errors squared. And this is the thing you're trying to minimize, the final line. So that's equal to the sum of the data, y, minus what comes out of the model, which will be m times x. And I'll put it like that, plus b. So you're trying to sum this over all the data. And the least squares, and this is squared, the least squares algorithm will find the solution for y and b from this. Now, it's going to be the sum of squared values minimized. And if you flip it exactly as you said, then what you would be trying to solve, instead of fixing the x part, you would fix the y part and try to predict x. So x tilde is equal to, say, n y plus c. And you solve for n and c using the exact same idea. Only down here it would say x minus ny plus c. These squares will solve for that one.
I think I have another simple idea to do this. Suppose I find the best is like y with respect to x, and then I find x with respect to y, and choose what I minus y.
Yeah.
So I have the r squared.
Yeah. Yeah. So that's the math behind it. You actually don't have to actually do this calculation, this part. That's built into the function that does the best line fit. Okay, but you can compare the output of the two best line fits. So remember, if you have perfect data, if this model is perfect, if y really is equal to mx plus b, then you could say that x is equal to y minus b divided by m. That should be perfect. But you're trying to fit data using a line model. And that line model turns out not to be perfect. Because it's not perfect, this isn't perfect either. And in fact, when you do the inverse to solve this version of the problem, what you get for 1 over m is not equal to m. Right? It's not equal to 1 over m. That's the point. So you multiply those two together, exactly as he said, If you have a perfect fit and you multiply the two together, it'll give you 1. Right? 1 over m times m should be 1. But if you fit this first and then try to fit this, the answer for the 1 over m part and the answer for m, those will be two different answers, and when you multiply them together, they won't give you 1. Why don't they give you 1? They don't give you 1 because the thing you're solving for is squared, it's not linear. Right? So when you have this square value in there, it makes it a nonlinear problem, so it's not proportional. I don't know if that makes sense, but that's the math behind it. Okay, so you put, there's 5 values of DC. You do this for each value of DC. So in the end, you'll have 5 slopes, 5 intercepts, 5 R-squared values. You write those into other arrays. So they go into their own arrays using the Voigt function. Okay. Then the next thing is, the main program should ask you for a design value of signal to noise ratio. What do you want for your signal to noise ratio? And then you're going to use the second Voigt function. So now we move ahead on the page. Yeah. And you'll have these slopes and intercepts from the first part, and the second Voigt function will take those answers and figure out the values that would give you the signal to noise ratio that you invoked. Okay. The main program then uses the Voigt function RB again, so that's the slopes and y-intercepts, to determine the slope and intercept of the GT of I values determined in part C versus the 5 DC values using this equation right here. Better? Did it help anything get something? Or you think, yeah? Okay. Okay, so it finds E1 and E2. They're unique for the chosen SNR. The program then uses the approximate and empirical relationship that cost is proportional to the product of GT and DC. That means they multiply by each other. And to try to find the optimum cost, GT and DC. So the cost would be something that's a constant of proportionality times the product. And if you substitute in the relationship here, take the derivative of cost with respect to DC, and equal to 0, that's how you find a minimum or a maximum. So you can solve and find out that this is the value of DC for the optimal cost. Then you can go back and get G. So you get DC first and GT second. It's a big project. Several steps. I hope it's an interesting project. Again, maybe you're not planning to go into electronics, but the same kinds of things that you're calculating in here, you could just change the words. You know, it could be that you're selecting, say, the thickness of steel and the depth of a beam to make a structure. So if you're trying to make a strong structure, and you're going to use a beam like this, right? How wide should it be and how high should it be? Because the higher you make it, the wider you make it, it uses more material. So it's going to be more expensive. So the cost is going to be somehow proportional to H times W. That's just like this. The cost over here is G, something proportional to GT times DC, right? That's obvious. The other thing that's obvious is the strength of this beam is going to depend a little bit on what these numbers are, right? So, you know, if you make a really skinny beam that's really deep, it might be very strong in one direction, not the other direction. So you need to be careful that you also have the right performance. So that's like that curve fitting of the data to see what kind of performance you will get for DC. Right? And as you probably know, people figured out a long time ago that actually the load is primarily vertical. Like it is on a lot of beams. Most beams carry a load mostly in one direction. If the load is vertical, this material in here doesn't help much. So it's much more cost effective to build a beam that looks something like this. It uses the same amount of material as that, but all the stuff in the middle gets moved up to the edges. Right, this is even called an I-beam. Because it looks like an eye. So if you go to a construction site, or even underneath a bridge or something like that, where there's a beam that's carrying a heavy load, it almost certainly has this cross-section shape. That's the way it looks, cut out on the sides. And did you calculate inertia in, you've calculated inertia in dynamics class? Right. So did you calculate inertia of area? Because that's the idea, right? The inertia of the area, this is just like these squares, but if you load a beam, as you know, this you probably had from Barry, I guess. But if the beam, I'm looking at the side of the beam now. If it gets loaded like this, then it naturally will want to bend, something like that. So the beam ends up bending down a little bit in the middle. In order for that to happen, the top has to get shorter. Where this bends down, it gets pushed together. So this is short, and this side has to stretch out. This is long. And somewhere in the middle here, it's exactly the same length as the original. This part in the middle that's the same length doesn't feel any stress. So it doesn't have any load. There's no load here. It's the same distance. This has a huge amount of stress because it's the one that's getting compressed the most. And this is the one that gets stretched the most at the bottom. So now if I look down the end of that beam with the cross-section, I can see why this makes sense. Because this is the part that would be getting compressed. Right? The load comes down like that. And this is the part that's getting stretched. And this part in the middle doesn't feel anything, just like this. So because it doesn't feel anything, don't waste your steel right there. There's no reason to put all the steel out here at the edges. Okay, so it's very logical. But as far as calculating the actual thicknesses and what you're going to put in there, you could make a program with more or less the exact same logic as that signal-to-noise ratio program. Calculate the total amount of steel, how it should be arranged in order to get the maximum strength. Good. You know, we do the same thing with rotation too. This happens a lot with satellites. In fact, one of the interesting things about rotation, this will probably work. There's inertia of rotation. Well, this is not exactly symmetric because this side's a little thicker, so it's not perfect. But there's three angles that this can rotate, right? It can rotate this way. It can rotate this way. And it can rotate this way, this way. Okay? So usually only two of those three are stable, one's unstable. The one that's unstable is usually the one in the middle. So when you look at this and you calculate this inertia is the moment of the area and the distance of the area. So it's an r squared, right? It's the distance out, it's a piece of mass times r squared. So it's like a least squares problem. Same with the inertia of this. If you calculate it, it's stable on only two axes. The one in the middle, it's not stable. So I don't know if I'm going to be good at this, but let me try. Okay, see that? It spins without any other rotation. Well, that one wasn't as good. Okay, now I'm going to try to do this one, where it spins this way. Not so good. Try it again. See, I don't think, part of this could be me that's not very good at it, but there's one angle that won't be stable. So the third rotation, I did that one, I did that one. Oh, the third one is this one. Yeah, that's to go this way. See, this one is the one in the middle. This one is the smallest. Yeah, I get myself confused. This is the smallest. This is the biggest. Actually, this one is similar. So, anyway. I think you can come up and try it as much as you want after class. You can try it now. Who wants it? I think if you try to flip it this way, you won't be able to get it to flip this way. It will always start to twist. Okay, so see how it twists? Okay, I can do like a half rotation, but even in a half rotation, it's already starting to twist. If you throw it higher, you can't get it to spin that way. It starts to wobble and changes into either this one or this one. Okay, because there are three axes, two are stable and one is not stable. So you also have to worry about that with structures. You can't just make this thing, in theory, it would be ideal if you could make that centerpiece be about 1 atom wide. And then way out at the end, have a huge flange, at this end have a huge flange. But there's a limit as to how thin that can be. It's got to have something in the center to be stable. Okay, long way. Sorry. By the way, can you back up just a minute? This statement right here, I'm not sure I would agree with this. Because you might want to be calling the infile in the middle of another program that you don't want to clear the variables. I'm not sure it's a great idea to always put clear at the top of every infile. Anyway, so let's go see your question. Okay, this shows, this isn't a great example, I think, because he probably should have made one of these numbers bigger than 1. But a subplot you can make, imagine a piece of paper. Here's the actual paper. If you call the plot command, well, that's a lot of piece of paper. Okay, much better piece of paper. If you call the plot command, normally what it'll do is draw one plot. Just like that. Right? Now if you use subplot, let's say you did subplot 3, 2, and I'll put the next one in the middle. Okay? If you make it 3 by 2, what that does is it draws a plot here, 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 and here. So on the same piece of paper, you would have 6 different plots. 3 by 2. Okay? Now the third number refers to which one? And I'm pretty sure it goes this way, but I'm not 100% positive. Maybe it goes this way. So if you put 1 in here, it's definitely this one. I think if you put, say, 4 in here, I think it's this one, because 1, 2, 3, 4. But it might be 1, 2, 3, 4. So maybe you have to try it and see which one it is. Okay? So a subplot command then will draw a regular plot, but instead of drawing it on a whole piece of paper, it puts it into a single piece of paper that has other subplots on it. So this one has 2. 2, 1, 1, 2, 1, 2. That's number 1, that's number 2. Everything else that comes after that subplot command is just a regular plot. It has its own title, it has its own grid, it has its own X labels, Y labels. Right? So everything on here is exactly like you can put on a single plot. And you get more than 1 on the same piece of paper. That's the idea. From a from a purely artistic standpoint, if you're trying to make a nice report, and you have multiple lines that you want to plot, you'll have to decide whether it makes more sense, say, to put 2 or 3 lines on the same axes, and that way you can compare them directly that way, or maybe you put each one on its own line over here. Just one at a time. I mean, it's up to you, I guess, to figure out the way that you think it looks best. Yeah, I think what he did in this one, he had data, so in the first one he plotted the data, and in the second one he plotted it as a blue line without plotting the individual data points. I think the only difference between these two is the R circle or the blue line. I think that's the only difference.
What is the Greek do?
Where are you looking? Sorry. Grid, that's these lines.
Can you make it straight line instead of
Let's see. Try help grid. Yeah. Actually, as long as you got it, why don't you go back and let's can you copy this statement? I guess you can't get that out of there. You can't copy that statement. Okay, so never mind. Go ahead back to the regular background. Okay, it adds major grid lines to the current axes. That's grid line. Grid minor toggles the minor grid lines of the current axes. Grid by itself toggles the major grid lines of the current axes. Grid AX uses axes AX instead of the current axes. So what that means is if you call grid, if you go back and look at the example for a minute, it put these grid lines on wherever the current labels are. But you don't have to have that. You can put the grid lines wherever you want. So in this example, if for some reason you wanted to have a grid line at 8.5, you could put an 8.5 grid line in. Or anything you want. You can put the grid line anywhere you want. So if you call grid, like he does here, if you call grid without any arguments, it toggles the grid lines. Do you know what that means? Toggle is a switch, on and off, on and off. Every time you call it, it turns it to the next value. If you call grid twice in a row, you wouldn't see them. The first grid turns them on, the second grid turns them on. The third grid turns them on, the fourth grid turns them on. When you call grid, it's a toggle to turn it on and off. Okay. I can't imagine why you would want to ever do that. In theory, you can. But that's what's meant by toggle. When you see in the help, if you go back and look at the help, it says grid by itself, that's no arguments, toggles the major grid lines. That word toggles, what that means is it changes the current value to either on or off. Whatever it is, it changes it to the other one. So if the grid lines were already turned on in the plot, and you put grid again, it turns them off. Like I said, I don't know why you ever want to do that. It doesn't really make sense to me, but okay.
that's not how we
Yeah. We're looking at the okay. Yeah, so, anyway, yeah, that's what grid is. Like I said, explains it. So one reason why you might want to call your own grid location, though, I mean, this could make sense. Let's say that you had, let me take a good example. Let's say you designed the heating system for this room, or the HVAC system for this room. So you decide, you calculate your prediction of what happens in this room on a day like today if you suddenly change that temperature instead of 16. Of course, that's very optimistic, right? The actual temperature is probably 30. But let's say that you set it for 16 and it actually kind of got close to 16. So maybe you end up drawing a plot. And you have a time axis down here and temperature up here, right? And so this is 30, that's where it starts, and it's set for 16, so here's 15, and here's 0. So your plot then looks something like this. That's over time as it gets cooler and cooler. If you call grid, if time is, say, 0, and then 10 minutes, 20 minutes, 30 minutes, if you call grid, it puts the grid lines in at these places. The ones that MATLAB picks for the labels on the plot itself, for the labels on X and Y, that's where the grid lines go. But you asked for 16. So maybe you'd like to see a line at 16 to see how your temperature is doing relative to what you want. So that in that case, you would use grid AX, and you can put in your own axes. All right, and that enables you to put the grid line wherever you want. So now you can call it and put another one in there at 16 as a comparison. You see pictures like that all the time. If you look at a plot of global warming, for instance, it might have a horizontal line that shows what the historical average of the CO2 concentration in the atmosphere was, and it shows how it's gone up way above that. So that historical average might not be a round number. Maybe it's 271 or something like that. If you drew regular grid lines, there wouldn't be a grid line of 271. It would be at whatever the round numbers are that are on the axis. Okay? Are you making 3D plots? No? Any other questions? Simple form of the model. Doesn't look so simple. This is interesting, because for a long time, probably people weren't very good at medicine. And as they started to get better at medicine, the early versions usually had the same medicine for everybody for a given disease. Right? So, it's basically the same pill. I mean, it's different medicines for different disease, but if two people have the same disease, you get the same medicine. So the future of medicine clearly is that everybody's body is a little bit different. So humans are slowly getting better and better at calculating exactly the best medicine for the same disease, but for different people. It will be something different. Right? The best medicine for Joe back there might not be the best medicine for Joe up here. So, this is kind of interesting because it takes into account body weight, metabolism constant, that would be for one person. Metabolism is the rate at which your body burns energy. The carbohydrate or fat inside your body. When you burn that energy, it's called metabolism. The drug release rate, that's something we can control the drug. Yeah, so I think that the younger you are, the more you're going to benefit from very rapid advances in headlines for news articles. One of them was about that simulating the human brain I was talking about. I think it was IBM, I'm not sure. Well, that was one piece of news, yeah, a couple of pieces of computer news. I think IBM is doing this simulation of the human brain. Didn't we talk about that in here? Yeah, well, I don't know if we talked about the IBM part of it, but we talked about simulating the electronics of the human brain. So the human brain is made up of cells that are called neurons. Each neuron is actually fairly simple to simulate, but the brain has billions of them. But the idea is, if we can simulate one, you build a factory, keep producing them. If you hook them all up the same as the neurons are hooked up in the brain, you could build a device, an artificial device, that has the exact same electrical properties as a human brain. And then in theory, at least, you could put your memories inside of it. It could think, it could feel, it could be happy, it could be sad, it could make jokes. I mean, it would be just like a human brain. So that's the idea. So we're a long way away from doing that, but there was an article in the news this morning that IBM has gotten a little bit closer. They did something new. The other big news is HP, Hewlett-Packard, has decided to get out of the PC business. So if you have an HP laptop or something like that, maybe someday it'll be in a museum. HP is not going to be in that business anymore. The company still survives. It's got lots of other products. They just decided they're not interested in that one. So they're not going to make any computers, any small computers anymore. Okay, what else? I'm completely flexible on the time. So if you want to ask more questions, that's fine with me. But don't feel like you have to stay. If you're done, we can all go home. It's totally up to you. So let's meet for tomorrow. Let's also meet maybe in the afternoon. So you have all morning to work. Okay. Is 1 o'clock or 2? Let's say. Why don't we say we meet at 2 o'clock again tomorrow? Is that a good time? Yeah. Okay. So I'll meet you in this room again tomorrow, 2 o'clock. And again, it's completely up to you. I don't want to. I'm here to help and try to answer questions. If you don't really have any questions, you don't have to come. It's up to you.